The cardiac cycle is one complete sequence of contraction and relaxation. There are a few basic pieces of information we need to know. One cycle is about 800 milliseconds long. Systole refers to cardiac muscle contraction. Diastole refers to cardiac muscle relaxation. And finally, the valves within the heart prevent the backflow of blood. This diagram is very complex. We're going to start at step F. From there, we'll work our way around the cycle step by step. We will start with the heart in ventricular and atrial diastole. Both the upper chambers and the lower chambers are relaxed and getting ready for the next round of contractions. During this time, blood is returning to the heart and filling the atria and ventricles. On the right side of the heart, blood is returning from the systemic circulation through the superior and inferior vena cava. On the left side of the heart, blood is returning from the pulmonary circulation through the pulmonary veins. These pulmonary veins carry oxygenated blood from the lungs to the left atrium. In this phase of the cardiac cycle, the pressure is higher in the atria than in the ventricles. This pressure difference keeps the atrioventricular valves open. Blood flows into the ventricles. This is referred to as passive filling because no cardiac muscle is contracting at this time. The flow of blood is due to the pressure of blood returning from the body to the heart. Notice that the semilunar valves are closed. You may ask the question, why are they closed? It turns out that after blood has been ejected by the heart into the major arteries, such as the aorta and the pulmonary trunk, there is a residual pressure that's relatively high. This pressure is due to the elasticity of the large arteries. During the time when the blood is being ejected from the heart, these blood vessels stretch, increasing in diameter. When blood is not being ejected from the heart, the blood vessels recoil elastically, decreasing in diameter. This decrease in diameter of the major arteries helps to maintain the blood pressure relatively high in the pulmonary trunk and the aorta. The pressure in the pulmonary trunk is greater than the pressure in the right ventricle. Likewise, the pressure in the aorta is greater than the pressure in the left ventricle. These pressure differences keep the semilunar valves shut. In the next phase of the cardiac cycle, the ventricles remain in diastole. However, the atria begin to contract. In other words, the atria are in systole. The contraction of the atria, which is referred to as the atrial kick, forces additional blood into the ventricles. In a person at rest, about 20% of the volume of the blood in the ventricles at the end of ventricular diastole, shown here, is due to this atrial kick. Next, the atria relax. They are in atrial diastole. At the same time, the ventricles begin to contract. They are in ventricular systole. This leads to an increase in blood pressure in the ventricles. Now the blood pressure in the left ventricle is greater than the pressure in the left atrium. This pressure difference forces the left atrioventricular valve to shut. The blood pushes against the flaps. The flaps are prevented from everting into the atria by the chordae tendineae and the papillary muscles, which contract. These are shown here. Similarly, on the right side of the heart, the right atrioventricular valve is prevented from everting into the right atrium by the chordae tendineae and the papillary muscles. When the AV valves shut, a sound is generated due to the vibrations of the heart resulting from these abrupt changes in blood flow. The closing of the AV valves causes the first heart sound, S1. You may have heard of heart sounds before. The heart makes a characteristic lubbed-up rhythm. The first heart sound, S1, corresponds to lub. In the next phase, the ventricles are still in systole and the atria are still in diastole. The ventricles are continuing to contract and the pressure in the ventricles is getting higher and higher. However, there is residual pressure in the aorta and the pulmonary trunk. This residual pressure is still higher than the pressure in the corresponding ventricle. For example, the pressure in the aorta is higher than the pressure in the left ventricle. This pressure difference keeps the aortic valve, the left semilunar valve, shut. Similarly, on the right side, the pressure in the pulmonary trunk is higher than the pressure in the right ventricle. Thus, the pulmonary valve, the right semilunar valve, is shut. As a result, all four valves are shut. Yet at the same time, the pressure within the ventricles is continuing to increase. In the next phase, partway through ventricular systole, the pressure becomes higher in the ventricles compared to the arteries. The left ventricular pressure is higher than the aortic pressure. The right ventricular pressure is higher than the pressure in the pulmonary trunk. Therefore, the semilunar valves on both sides of the heart open and blood is ejected. The blood ejected into the aorta goes into systemic circulation. The blood ejected into the pulmonary trunk goes into the pulmonary circulation. Because the blood leaves the heart during this phase, it is called the ejection phase. In the next phase, the ventricles begin to relax. They are in diastole. The pressure in the ventricles drops. In this phase, the semilunar valves close. They close because the pressure in each major artery, the pulmonary trunk and the aorta, is higher than the pressure in the corresponding ventricle. To understand this phenomenon, let's look at the left side of the heart. In the previous phase, blood was ejected from the left ventricle into the aorta. The aorta is very elastic, so it is increased in diameter. Now, by elastic recoil, the aorta starts to decrease in diameter. This passive elastic recoil helps to maintain the blood pressure in the aorta relatively high. Thus, the blood pressure in the aorta is higher than the pressure in the left ventricle. This pressure difference keeps the left semilunar valve shut. Similarly, on the right side of the heart, the higher pressure in the pulmonary trunk keeps the right semilunar valve, this pulmonary valve, shut. Notice that the AV valves are also shut. They remain shut because even though the ventricles are relaxing, the pressure within each ventricle remains higher than the pressure within the corresponding atrium. So during this phase, all valves are closed. The atria continue to receive blood, therefore the pressure within the atria is gradually increasing. The sound that is associated with the closing of the semilunar valves is the second heart sound, or S2. This sound is the dup of love dup. In the next phase, the ventricles continue to relax. They're in diastole. At this point, however, the AV valves have opened. They have opened because the pressure within each atrium is greater than the pressure within the corresponding ventricle. You might ask, why is the pressure higher in the atria compared to the ventricles? The reason is because blood has continued to flow back to the atria, increasing the pressure within them. At the same time, the ventricles have continued to relax. As soon as the atrial pressure became higher than the ventricular pressure, the AV valves opened. Now we have returned to our starting point. Recall that at this starting point, the atria and ventricles are relaxed, and blood is flowing into the heart passively. We have now completed one full turn through the cardiac cycle. We started with the atria and ventricles in diastole. Now we've returned to the point where they're in diastole again. I hope that this video was helpful. I have some questions at the end of this video you can use for self-study. Thank you very much.